Our final lesson in stoichiometry is heat stoichiometry. Now we use the word heat to mean energy. So our balanced chemical equations can tell us not only a mole-to-mole ratio, but they're also able to tell us how much heat can be released or absorbed by a chemical reaction. These are called thermochemical equations. Another word for heat is enthalpy, and we symbolize it with delta H. Our change in enthalpy is a measurement of how much heat is released or absorbed by a chemical reaction. An exothermic reaction has a negative delta H, and the heat is released as a product. This would be a reaction that is warm to the touch. If you had the reaction occur in a glass beaker and you felt the glass, it would be warm to the touch. It is releasing energy. The reason delta H is negative is you have to think of that energy as coming out of the reaction. The reaction is a system, and the system is losing the energy. So, in that sense, the delta H is negative in regards to the system. An endothermic reaction absorbs energy. Heat is taken in as a reactant. If you were to feel this test tube, the test tube of a reaction occurring endothermically, it would feel cold to the touch. That's because energy is being taken in to drive the reaction. And those delta H's are positive, in addition to the heat in the system. Some examples. So the acidic anhydride, again, that's an acid without water, of sulfuric acid is sulfuric trioxide. The delta H, or change of enthalpy for the reaction between 1 mole of sulfur trioxide and water, is negative 129.6 kilojoules. First question, is heat a reactant or a product? Part B, write the thermochemical equation for the reaction. Part C, how much heat will be released when 583 grams of sulfur trioxide reacts with an excess amount of water. So here's our stoichiometry. Question A, is heat a reactant or a product? Well, we just simply need to take a look at the sign on the change of enthalpy. It's negative 129.6 kilojoules. That means it's a product. To write the thermochemical equation, well, heat goes on the side of the products. If it's a product, it goes on the right. Notice it's not negative in the equation. It should never be negative in the equation. If it's a negative delta H, that means it goes on the product side. If it's a positive delta H, it means it goes on the reactant side. But never when it's written out in the equation should it be positive or negative. All right, now the stoichiometry part. Again, we're looking for how much heat. We measure that in kilojoules. It's our measurement of energy. When 583 grams of sulfur trioxide. So first step, as always with our stoichiometry questions, we need to go from grams to moles. So add up 1 sulfur, 3 oxygens, that's the molar mass of sulfur trioxide. Now that I have my mole ratio, I can use my balanced chemical equation like I would normally use it and say 1 mole, the implied 1 in front of SO3, 1 mole is equal to negative 129.6 kilojoules. Again, negative because it's a product. I crunch the numbers then. 583 grams of sulfur trioxide is going to yield so many moles, and so many moles will yield so much energy. With proper significant digits, I should expect negative 944 kilojoules of energy would be released from this reaction if I started with 583 grams of sulfur trioxide. One more example. Carbon dioxide decomposes when 43.9 kilojoules of energy is added to it to produce carbon monoxide and 1 mole of oxygen. Again, first question, what is the delta H for this reaction? Second question, write the thermochemical equation for the reaction. And part C, how many grams of carbon dioxide can be decomposed by the addition of 222.2 kilojoules of heat? So this question is giving us an amount of energy and asking us to figure out a mass of carbon dioxide that we can decompose. So part A, carbon dioxide decomposes when 43.9 kilojoules of energy is added. Added would be, it's a reactant. It's going into the equation. It's an endothermic reaction. So we have a positive delta H, 43.9 kilojoules. Part B, write the balanced chemical equation, thermochemical equation. Carbon dioxide yields carbon monoxide and oxygen. And because our delta H is a reactant, it has a positive value, we will put it on the reactant side. Per 2 moles of carbon dioxide, it's going to require 43.9 kilojoules of energy. So finally then, let's go ahead and solve. If we have 222.2 kilojoules of energy, how much carbon dioxide can we break up? First step, we're going to go from kilojoules to moles. And we can use our balanced chemical equation. It'll take 43.9 kilojoules to break up 2 moles of carbon dioxide. Now that we have our moles of carbon dioxide, we go to grams of carbon dioxide. Again, the question's asking, how many grams of carbon dioxide? We crunch the numbers, and we get, with significant digits, 446 grams carbon dioxide can be decomposed from 222.2 kilojoules of energy.